start streaming. So we should be recording now. Does it matter whether I use the mic or not?
Oh, this looks interesting.
That's for my other class.
What class is this so I can join it?
It's assembly language programming.
All right, then I'm signing.
And most of you cannot avoid it. So you can take it from me or you can take it from another campus, but you cannot avoid the class itself.
No, I'm gonna take it under you now. This actually looks fun.
I would not make any conclusions until the end of the semester.
I'm already dead inside.
I'm skeptical. I'm skeptical of everything, including myself.
Wait, it's like I said, this is my own existence, and then you just disappear. And they come back. I'm skeptical of my disappearance.
I'm skeptical of my own skepticism.
Wait. Yeah.
Is my skepticism actually good, beneficial, or not? So, alrighty. So we are pretty much done with functions as sets. Okay, so I'm just hoping that we got this module down. Okay, I just scroll all the way to the end because that's where we talked about what makes a function, which is this not so much equation, a statement. Okay, so this particular statement here is basically stating if you can find me a set F, okay, which is a set of two tuples, and it is a subset of the domain Cartesian product with the codomains, and F satisfies this requirement, okay, then F is a function. Okay, so that's the bottom line from the lecture on Monday. Are there any questions about this one or the meaning thereof? Any questions? All right. So if there are no questions, I'm going to move on. And we also talked about why we kind of need representation of functions like this, because in order to talk about what a sorting subroutine is supposed to do, or what a sorting algorithm is supposed to do, we have to make use of the idea of a function, because we need to make sure that whatever the k values are, the constants at the beginning of the as the input condition of a sorting algorithm. When the sorting algorithm is done, every element, okay, at the end of the execution, the value of every single element has to map to one and only one of the original values. Okay, so that makes it necessary to use functions the way we do in this class, which is kind of different from most of your other classes. Like in calculus, your functions are continuous, right? You can actually make a shape out of it. You can plot it. But in this class, we don't plot functions because our functions are not used for those purposes. Okay. So, are there any questions before we move on to the next slide, where we talk about the three different properties that we can qualify functions for? No questions? No questions about set theory or terminology thereof? Yep.
I have a question about notation.
Okay.
Since the bars mean cardinality,
Which also, yeah.
do we have a use of just one bar?
The single bar is used if you look up. Oh, just right here. It can be used to separate the format of an element as opposed to the qualification of what should be in the set. So that is also a bar. So the bar has multiple meanings. But when bar is quote unquote infix like this, it means such that, or the element has to satisfy the following requirement. When bar is used as what we call I'm looking for the word, but brackets, okay, for the lack of a better word, a pair of brackets, then it means cardinality. How many things are inside either the set, or it also applies to tuples. Okay. So are we okay so far in terms of terminology, the basic concepts of what a function is, and operations that we can perform? We can perform with set operations. Yep.
Just one question. It's just about the symbols. The one with the C and the line under it.
Huh?
I was just asking a question about the symbols.
It's a subset of. That is subset of, and then the one without an underline is proper subset of. Yep. Okay. Cool. And I was expecting me to be a little bit louder because I forgot to turn on the amplifier. Yep. Go ahead.
Could you read that line out loud? Like, how would you?
You mean
say
this line
the
here?
One for all elements E.
Okay.
That are elements of the set of X.
Okay, so it's going to get a little messy when we read this out loud because it has a nesting in it. And you know, the natural language is not very good with indicating how things are nested, right?
I just want to hear if I have
Okay.
it correctly in my head.
So this is basically saying for each element E in X, and X is the domain of the suspected function that we are talking about. Okay, the following requirement has to hold true. Okay, and then we explain what the following condition is. So the following condition is if you construct a set of two tuples from F itself, and the first item of each two tuple has to start with the E, then the cardinality of that set has to be 1 and only 1. So it's really kind of long and difficult to understand. The other way to say that is really just to say that every element in the domain has to map to one and only one element in the codomain through the use of F. So that's the kind of easier way to understand it. So is that helping? Or?
A little bit, yeah.
Okay. Any other questions? And this is also why we use mathematical symbols. It's because it is really difficult to use natural language to express some of the concepts, and that's why we use mathematical symbols. And if you feel, in this class, if you feel like, oh, I've never seen so many obscure mathematical symbols, nested in weird ways, before, it's okay. You're not alone. And I'll tell you a little story. We'll digress a little bit. When I was in graduate school, I was in UC Davis graduate school when on my way to get my PhD. My dissertation, okay, just the name of that is a little bit strange. It is called a stochastic admissible heuristic search. Okay.
What?
Stochastic admissible heuristic search. And my entire dissertation is not about writing a program. It's not discovery of an algorithm. It is about the property of a solution to a kind of problem. I don't care how you find the solution. I'm only describing properties of the solution. So that is the kind of dissertation that I worked on. The original version, like version 1 of my dissertation, which contained everything that I thought was sufficient, in the entire dissertation, it was about 50 to 60 pages long, which is shorter than most master's thesis. It's really short because it's mostly just the mathematical symbols that you encounter in this class, and then some a little bit more obscure ones. So I turned that into my my dissertation committee, okay, which is made out of 3 professors. And those are like, one of those is a really long-time professor, teaching out the analysis of algorithm. So mathematics is nothing new to this professor. So the professors came back to me and go like, Tak, you have to use English. Because the entire thing is like symbols. The only time I use English is, okay, observe the derivation of blah 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 blah, right? Okay, and then it follows that blah 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 blah, and they're all mathematical. So I asked my professors, go like, but if I move all my proofs, the actual symbolic proofs, to the appendix, because that's what they're suggesting me to do, then there's nothing left. They just told me you have to find a way to fluff it up, basically. So you're not alone in this class when you say, oh, way too much, mathematical symbols. Well, you're not alone. my professors, at UC Davis agreed. All right, so that should make you feel a little bit better. All right, so we are moving on in terms of the notes. We are moving on to properties of functions. So given that something is a function, what can we say about the function? So there are these three words that are applicable to describe a function. So the question is it injective, is it surjective, or is it bijective? So these three, the first two are sort of related, but the last one is definitely related to the first two. So section 2 here explains what injection is, and I'm still waiting for my voice to get a little bit louder. Okay.
What was the other one? It was injections, surjections, and the third.
It's in the title of the page. Yep. So it's in the title of the page right there.
I was just missing bijection.
Okay. So all right. So remember, everything that I use in this class, at least the class notes, they're all on Canvas already. So it really is helpful for you guys to kind of read ahead of me a little bit. You don't have to understand everything. If you don't understand something and you think it is probably important, you can just kind of jot down the question and ask that question in class when we get to that point. But it is important that you read ahead of time so that you are familiarized with the terms and in what context are we talking about these things. All right, so in an injection function, I'm just reading my own words here, aka an injection. So injection is the same thing. It's the same thing as an injective function. So sometimes we say it's an injective function, other times we just say this is an injection. Each element of the domain in such a function maps to a unique element in the codomain. Let us assume the function of interest is f, which maps the domain x to the codomain y. Then an injection has the following additional property. Okay, so let's see what this is saying. Okay, and we'll try to use English to describe it first. So we are basically saying for each p in x, okay, if you consider each element p in x, which also means we have to consider every element in x. Whatever is following has to be true for every element in x. Okay? That's why we have the for all instead of the there exist. If I say there exist, then if at least one element in x is like this, then the whole thing is true. But when I use for all, it means every p in x has to satisfy the following requirement. Is that okay? All right? Okay. So by the time we get to the second part in the parentheses, p is already known to be an element in x. In other words, we have quote unquote bound the value of p to a particular element in x. So now, what do? Now we say for all q also in x. This p and this q here, they are not related. They could be the same thing. We could pick exactly the same element, as p, and then we pick the same element as q. So p as a variable and q as a variable can bind to the same element in x. That should not be a problem, okay? Well, it should not be a problem because the first thing we do here is to say p not equal to q implies the following, which also means if p and q so happen to be the same, what happens to this portion of the statement? It's true, because if p and q are exactly the same thing, p is different from q is going to be false, but if the first part of an implication is false, the implication itself is true. So we are really only interested in the second part if p and q are in fact different. Are we okay so far? So we are now down to the last part, which is the actual really important part of this entire statement. If p and q are different, then f of p should also be different from f of q. That's the bottom line. Are we doing okay so far with this? Yep.
So the only way that f is true, so p is different from q, and p of f is not different from q of f.
So the only way to make this false is for p and q being different, but they map to the same thing in the codomain. So f of p equals to f of q despite P is different from Q,
Yeah, which is not gonna happen.
which can happen to certain functions. Yep.
If all of P is equal to, I was wondering if you go over the statement one more time to make sure I got it down. So it's you saying all of P, right? True. The element of X, right? If all of the elements of Q is an element of X, then that means that that statement is false, right?
Okay, how about this? I'm gonna try to okay. So I'm gonna try to explain this using a block of C code. Okay.
Okay.
Is that okay?
Okay.
All right. So the block of C code in this case is going to be a little bit funky because it's not, we don't have set notation in C and C++. So all I can do here is to kind of imitate, okay? So we're going to say, let's see if this works, okay? If it works, great. If it doesn't work, then we'll find another way to explain it. Okay, I just want to resize my notepad. Okay, resize. There we go. Because what I want to do is to show the requirement here and then turn this into quote-unquote C code that has the same meaning. Okay, so we'll say for, okay, P, okay, semicolon because there's no initialization for P in X, okay, P equals next element in X, okay. So I understand that C doesn't really has the notation of a set notation, but we'll just kind of use it kind of like this. Then we have a nested loop here. So this is the outer loop. There's an inner loop. So the inner loop is going to be about the same for, there's no initialization, Q in X, Q equals to next element in Y. Sorry, I used the X incorrectly here. Now, if you want to put something into the initialization, you can kind of say that, I really hesitate to do it. But if you really want to do it this way, you can say first element in X. The reason why I hesitated is because in a set, there's no real ordering. You can pick anything in as quote-unquote the first element. But because we're turning this into sequential code, so we are going to, there's got to be a first element that we are going to evaluate. So that's why I kind of hesitate to do it this way. But if you really want the code to look right, I suppose you can do it this way. So first element in Y, okay? But the point is we're dealing with a nested loop here, okay? So we have a nested loop, and then inside here is what we're evaluating. So in addition to all of this, I'm going to use, this is plain C, so we have no Boolean types. So we have a result here. Because we are also using for all, we'll just say that, we're assuming the answer is true, unless we can prove otherwise. So inside here, I'm going to say result equals to result and the following. Okay? In other words, in order for the entire result to be true after the loop itself, whatever is next to this ampersand operator has got to be true for every way to pair up P and Q. Is that okay? All right? So the rest is kind of easy, okay? Because the rest here, okay, I'm putting parentheses around the actual condition, which is going to resemble this part here. Except in C and C++, there's no implication. It's not a big deal. Implication, X implies Y is really the same thing as not X or Y. Okay, so we can just imitate that. Okay, so it is just not X, P, not equal to Q, and then we have a disjunction or, and then the rest. Okay, P, F of P does not equal to F of Q. Okay, and I use extra parentheses, just to emphasize, what we are ORing in this case. So whatever the result is, okay, result is the value of the whole statement. Okay. So is that better? I mean, does it illustrate the concept of for all a little bit better? using this method? Yes, no, kind of. Now, there are certain programming languages that has a special construct of for each. So those particular languages like Python, PHP, it's really kind of cool because you can just say for each p, and then you use x, in the first one in the outer loop, and then you say for each q, and then you use y in the second in the inner loop, and it will automatically pick up the elements or so-called elements in each. Usually it's called a list, okay, or or an array. Yep.
For the first part of that conditional thing made in parentheses, the not p is not equal to q, could that just be p is equal to q then?
Yep. You can get rid of the not
But you
and
could
just
show that because
yeah.
it implies
Yep,
that-
because I want to make it clear that when you deal with implication, you're negating the first part of the implication, and then you or the second part just the way it is. Yep. So is that helping? Okay, all right. So with that out of the way, so I'm going to assume that we understand what this statement means at this point. Okay, is that okay? All right, cool. Or it can also be stated as follows: counting the number of elements in the domain that can map to each element in the codomain. Okay, so you look at this thing here and go like, yeah, we have seen something like this before. We have seen something like that before, but not exactly the same. There are major or important differences between what we saw earlier compared to this one. Yes?
Sorry, again, for the code that you've written,
Uh-huh.
is q, should q also be in x?
No.
No?
Q is an element in the codomain. That's why Q is in Y.
Okay.
Now, there are cases where X and Y are really the same set. That's possible. But, if I say X is the domain and Y is the codomain, then I have to separate and say, Q is in Y and not in X.
From the above code there, it made it seem like after p was, like the f of something is a codomain? Or
Oh, you're right. Okay. I messed up. Sorry.
Alright, okay.
Yep, I messed up because, this really should be X too. I messed up that one.
Syntax error.
Not syntax error. This is actually semantic error.
So that's all right. Then I'm gonna go jump off.
But it is wrong. Okay, I stand corrected because Q is another element from the domain, and we care about where they map to in the codomain. So f of p is in the codomain, f of q is also in the codomain, and we want those two to be different if p and q are different. So I stand corrected. Good point. Good job. Is that okay? Most other professors would just say, well, I'm just checking to see if you guys are awake, right? I just messed up. That's plain and simple. Is that okay? All right, cool. All right, so we want to look at the second way to look at injection. So that's the second form to look at injection is to look at everything in the codomain this time, okay? So for each element in the codomain, you're now asking the question, okay, so let's evaluate what is in the parentheses. We are looking at impromptu, sets, a impromptu set that is, including all the elements of the following property. Each element is a two-tuple PQ, and Q is already determined from the outside. In other words, when we say for each Q in Y, we are binding Q to a particular element in Y already. So Q is already fixed. So what is a variable in this case is P. So we are basically looking for every single two-tuple that ends up with the second part being Q. Is that okay? That's what this set is about. This set contains every element in F such that Q, which is bound by the outer quantifier, so that the second item of the two-tuple is Q, but the first one can be anyone. Okay, find me all the two-tuples in F where the second item is Q. Okay, and then we look at the cardinality. And we are basically saying that cardinality has to be less than or equal to 1. which means it can be 0 or 1. So what is that saying? The bottom line is it's saying each element in the codomain cannot be mapped from more than one element in the domain. Is that okay? And that is basically saying the same thing as the previous statement. Yes?
So that means the codomain can have values that aren't mapped to by the domain?
Yes. You can have things that are just sitting around idling because nobody maps to them.
Okay.
That's perfectly okay. It is still a function because it's still as long as the requirement of a function is still satisfied, it is okay. Is that okay so far? So now we want to look at some examples. Yes?
That statement you said, I forgot what you said. Just reiterating, like,
You mean with this one?
yeah, what I mean.
It means for each element in the codomain, the number of elements in the domain that map to this element in the codomain can only be up to 1.
Okay.
It can be 0, but it cannot exceed 1. Okay, so we're going to take a look at some examples now. And we'll take a look at an example, and I can use just the text editor. That should work well for this. Okay, but I'm going to scroll stuff off the screen first, just so that it doesn't interfere with these examples. So I'm going to use X as my domain, just to be consistent, and we'll use ABC again. It doesn't really matter. I mean, it's just for convenience. Y is 1, 2, 3, and now we say that F is a function that maps from X to Y. This is just a notation indicating that F is a function, X is the domain, and Y is the codomain. That's all it's saying. Okay?
Why is the domain, X is the domain, Y is the codomain?
Yes. And now we want to define the actual content of F. So F is a set of 2 tuples. So I'm just going to give you an example here. A1, okay, most people would think of this one first, so we'll deal with it first. Okay. This is one function, right? This is one function to map from X to Y. Is that really a function? Does every element of the domain map to one and only one element in the codomain?
Yes, so.
Okay. Is it injective?
What does he do? Oh, yeah, it is. I'm guessing.
Okay. Why is it injective? Because there's unique pairing. Very good. So if you choose 2 different elements in the domain, they map to 2 different things in the codomain. Okay, that's one way to say it. And then the second way to say it is to say, if you look at everything in the codomain, it is mapped from the domain once or none. Okay. In this case, it's once. Okay. Okay. So that is cool. So so this is a function, and it is injective. Okay, so we'll take a look at the second one. A1, B1, C1. First of all, is it still a function?
Yes.
It is still a function because
Each one is unique.
no, it is not unique this time.
Okay.
Yep.
Elements in the domain are more than one thing.
Each close. Go ahead.
Each element in the domain is equivalent to the same element in the domain.
But that doesn't make it a function. That's an extra property, but what makes it a function? Yep.
You have one of each in the domain and only one, like that maps. You can't have you can't have like A1 and A2. You can only have one A, one
Okay.
B, one C.
So it still satisfies the requirement of each element in the domain maps to one and only one element in the codomain,
Oh, it has to match the codomain.
right? But they all map to the same thing in the codomain. It's okay. I only said that every element in the domain has to map to one and only one. I didn't say unique element in the codomain. So it is still a function, okay? But is it injective?
No.
It will fail the injection test. Both of those tests will fail, right? Because with the first one, it would fail because if I pick 2 different things in the domain, let's say one is A and one is B, okay? They're different in the domain. what do they map to? They map to 1 in the codomain, which is the same thing. So it fails the first test, okay? What about the second test? I look at everything in the codomain, okay? I don't even have to look at 1. I can look at 2. 2 is fine, right? 2 is not mapped to, which means that the cardinality of that set, or if I count the number of elements in the domain that maps to 2, it'll be 0. Is that okay? Is 0 less than or equal to 1? Cool, not a problem, right? Yes, 3 would have the same story. What about 1? How many things in the domain maps to 1? Map to 1. 3 things. Is 3 less than or equal to 1? No, it failed that test. Is that okay? Okay, so let's check out another one then. We'll have f equals to, okay, this time we'll change the set a little bit. Okay, so we say x is ABC, and this time y is 1, 2, 3, 4. Or we can scream back as a class. Okay, so A1, B2, C3. Okay.
That's an injection function.
Well, that's what I'm going to ask. Before I ask whether it is an injective function, I'm asking, is it injective? You know, if f maps from x to y, is it injective? Can we claim that f is a function that maps from x to y? That's the first question. Does it satisfy the requirement of every element in the domain maps to 1 and only 1 element in the codomain?
Yes.
All right, so it is a function. Once we know it is a function, then it makes sense to ask the question, is it injective? What do you think?
Yes.
It is also injective. Very good. Because if I choose 2 different elements in the domain, they would map to 2 different things in the codomain. What about that weird thing 4 in y? It's not mapped to. It's okay. That's not a requirement to be injective. So are we good so far?
There's a lot to write.
But that's why it's being recorded. But you're one of those people who
I gotta have it
want to
down.
make sure.
Yeah.
Yes. But have you watched the YouTube?
I get home late, so I have to do it when I wake up, because I get home like at around 10, 11 at night.
Okay.
Yeah.
But go ahead and try out the video, because if you watch the video, you will find out that hey, it's even got the voice and everything else. So okay. So I think we are pretty much done with injection for now. So we're going to move on to surjection. So surjection is a surjective function, or known as a surjection, is a function where every element in the codomain is mapped to. Okay. So this time I'm going to do the reverse way. Okay, I'm going to use examples first, and then we go back to the mathematical notation of what qualifies as a surjection. Okay, because I want to make sure that you guys can go in either direction. Okay, understand the meaning first, and then derive the mathematical notation, or go the other way around, understand the mathematical notation, and then find examples to illustrate it. Okay, so I'm going to use pretty much the same thing over here. So I'm just going to do a copy and paste. And I tell you that f is already a function, so don't that it's not a question. So the question is it possible for this f to be surjective?
No.
Surjection means everything in the codomain is mapped from at least 1 element in the domain.
No.
No.
Why is that not possible?
Because there's more things in the codomain than the domain.
Exactly. Yep. There are more things in the codomain than there are things in the domain, so that makes it impossible to have everything in the codomain mapped to. Yep.
Could it be surjective if it's not a function?
No. Surjection only applies, or surjective only applies to functions. That's a good question. Okay, so we can say this cannot be surjective. Okay.
So for it to be surjective, they has to have the same amount of elements inside.
No, I didn't say same.
Okay.
Cannot be more.
Can Cannot be more than a subject.
Yep. So if you look at the cardinality of y, if that is greater than the cardinality of x, then f cannot be surjective. Okay? It makes perfect sense, doesn't it? Prove it. Okay, so you can the argument is there. Okay, the argument which we all understand intuitively is correct. Okay, because there are more things in the codomain than there are things in the domain, and as a result, you cannot have the function being surjective because something in the codomain cannot be mapped to. Okay, it makes sense intuitively, but can you prove the theorem? Can you prove the statement? How do you prove that statement? Why am I so obsessed with proving a statement? Let me tell you another story. From my graduate school days. Okay, I'm old and I still remember these things. So my dissertation was based on the work of a master's thesis. My advisor said, okay, so read this master's thesis and then use it as the basis of my dissertation. So I can basically, my dissertation becomes a continuation of the master's thesis, which makes sense, right? You don't want to reinvent the wheel all the time. You want to build upon the work of somebody else. So there was a theorem in the master's thesis that my advisor just said, okay, so since that is proven already, you can just build on top of that. And then for a few weeks, I was working on my dissertation based on that particular theorem. And then in 1 week, I just thought, this doesn't feel right. It's just a gut feeling that this is not clear to me that the theorem is true. It just wasn't clear to me. So I went and tried to prove it myself, and I couldn't. I could not prove the theorem. So I went back to my advisor and go okay, is there an actual proof of this theorem? Can I read the proof so that I can convince myself, yes, I can build my dissertation based on this particular theorem? Then my advisor said, okay, just check out that master's thesis. It's proven in the master's thesis, right? So I went back and read the master's thesis, and the theorem was proven by obviously blah 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 is true. I go no, it's not obvious to me. Maybe I'm just slow, but it's not obvious to me. So so then I spent I went back to my advisor again and go no, there's no actual proof. Then my advisor said, oh, just move on. It's okay, it's done. So I spent an entire week to come up with a counterexample, and I did. So a counterexample is an actual example to show you that a theorem is not true. Okay? So I came up with a counterexample. I went back to my advisor and I showed my counterexample. Okay, this is how we can set up the problem, and then that theorem is not true anymore. And then the only word that came out of the mouth of my advisor was, oh. But that was not it. That was not the entire story. I went back to the AI lab and I told the guy, another master's student, whose thesis was based on the same thing, and he already spent 3 years on that already. So I told him, and I just said, hey, you know what? I just told Armand that this theorem is actually not true. I proved that it's not true. Here's the counterexample. And he just went ballistic. He just went ballistic because he basically used 3 years to work on his own dissertation, not dissertation, but thesis, based on that theorem that turned out not to be true. And the not so funny part, funny but not so funny part was the thesis committee of that thesis that had a unproven theorem that turned out to be false is the same people on my own committee.
Oh my goodness.
And they wanted to move all my proofs to the appendix.
Hold on, so what did the guy end up doing? So what did the guy end up doing?
I hope he himself.
I do not know. I did not know. I didn't ask. I think they probably gave him a pass, okay, because of the theorem, proven incorrect. They just kind of went a little bit easier. I don't know. I don't know exactly what happened to him. I know that he graduated.
Okay.
Yeah.
Oh, okay.
So they did not pin it on him. That would be so totally unfair.
What happened to the original guy who made that theorem? Did they take
Well, he graduated already. I suppose you can revoke, a degree once you award it, but it's very rarely done. Typically, and in this case, the part of the responsibility, or I would say that most of the responsibility rests on the shoulders of the professors, the committee itself, because they are supposed to be the expert in the field. They should have caught it, and they did not. So I guess they didn't want to open that can of worm. Now, of the 3 members of the committee, other than one guy who had worked at UC Davis for a long time already, the other 2 were on tenure track, and neither got tenure. But not because of this. When you work as a professor at a UC like UC Davis, whether you get tenure or not is not based on how you teach your classes. Okay, every single student can say that we like this professor. Okay, but if you're not producing any research paper, if you're not getting any research grant, you're not gonna get tenure.
Oh, okay. That makes a lot of sense.
And here we don't do any research, so there's no such thing.
They
So-
just look for fun.
Huh?
They just look for fun.
Here
UC Davis.
at UC Davis,
They're all theoretical, so
they're more on the theoretical side compared to CSUs and particularly community
Yeah,
colleges.
but they have like undergrad students, and they need professors. They shouldn't say, "Oh, you don't make."
No, they have undergraduate students, and they need someone to teach those classes,
Yeah.
which is different from they need professors to teach those classes.
research funding.
So a lot of times, especially when they receive a lot of funding, for a successful department, when they receive a lot of funding for their research programs, they would be hustling, bustling with doctoral and master students. So the professors would be kind of busy just managing the graduate students. So they would send a TA or a graduate student to teach the classes instead of having the professors to teach the classes. Or they would have a lecturer, which is a instructor of a lesser rank, to teach the undergraduate classes. Yep.
Did you end up contacting the guy that made the original theorem that you referred to before?
No, I did not.
Okay. Well, as long as he's
That was
doing
not.
all right, that's
no,
one thing.
that was not my intention. My intention was not to direct anything to anyone. My intention is really just to seek the truth, right? That's a very INTP thing. If you read up on personality types and stuff like that, INTPs are the kind of people who just wants to know the truth, but I don't want to pin it on people. That was not my intent. Okay. Looks like you got a question.
No, I'm just stretching my wrist. My wrist hurts.
Okay, because you got that Ultraman, thing.
I love Ultraman.
Yeah. Okay. So how do we prove that theorem? Getting back to proof, right?
How do we prove
We
it?
don't have the tools to do it just yet, okay? Because the best way to prove that particular theorem, that if the cardinality of the codomain is greater than the cardinality of the domain, then F cannot be surjective. The best way to prove it is proved by contradiction. Okay, you guys just heard of counterexample to prove something wrong. So proof by contradiction seems to be kind of the same thing. Well, it's actually a very different thing. Okay, so when we get to that point, if you guys still remember, you can ask me. Okay, you kind of mentioned that we can prove this particular theorem using proof by contradiction, and I can go back and prove that by contradiction. Okay, because it's a very nifty way to prove something. Okay, it's really, really cool. Okay. So now we go back to the mathematical way of saying what is a surjection. Okay. So to show that something to show that f, which is known to be a function already, is also a surjection, this is how we do it. Okay. There are 2 ways again. For everything in y, okay, not in x anymore. Okay. For everything in y, there exists at least one thing in p so that f of p is q, and q is the one thing from the codomain. That's it. It just says there exists, right? So everybody can map to it, or a lot of things can map to it. Is that okay? The first kind of definition of what makes a surjection a surjection. So there's also a second way to do it. The second way is kind of resembling this one over here. When you compare this statement versus this statement here, there's only one minor difference. And the minor difference is the less than or equal to is now greater than, oh, here, this is load up the screen. It becomes greater than or equal to. Okay, that's the only difference. Yep.
So the domain can be greater than the codomain.
The domain can be greater than the codomain in the case of surjection. Yep.
Oh, surjection?
Yep. You can look at extreme examples too. So let me give you an extreme example. So the,
You said the domain can be bigger than the codomain?
Yep, in surjection.
I need it.
But that by itself does not guarantee surjection either.
Oh, Professor.
Yep.
The way that you'll break this out, so does the domain always go on top and then the codomain goes at the bottom, or what's up we want to
Oh,
break?
you mean when I defined it? No.
So-
It's just an example. So the ordering does not matter in this case. Yep.
So when the domain is bigger than the codomain, one of the elements in the domain can't have a element in the
That is correct. So that means, okay, so we talked about some concept that is related to that, right? We talked about injection. When the cardinality of the domain is greater than the cardinality of the codomain, then injection is guaranteed to be false. Cannot be an injection anymore. Does that make any sense? So once again, to prove that, we can use proof by contradiction, but we haven't really talked about proof by contradiction yet.
But
Mhm.
wouldn't, if the domain is bigger than the codomain, wouldn't that make it not a function?
No, because everything can map to the one same thing in the
Well-
codomain.
Well, if it's a codomain and it doesn't have an element, if the domain doesn't have an element in the codomain, that's not a function anymore, right?
Okay, wait, hold on. Say that one more time.
So when you have you have 4 elements in the domain, and you
Uh-huh.
have 3 elements in the codomain.
Right.
3 of the elements in the domain map to 3 elements in the codomain, but one of the elements in the domain doesn't map to a codomain. That's not a function anymore, right?
If it is not, but you can remap to one of the things in the codomain. That is okay.
Okay, but if you remap to one of the elements in the codomain, that's not surjective anymore, right?
That's why that is still surjective. It is not
still surjective.
injective, but it is surjective.
Okay. So you can have an element in the codomain mapped twice if it's surjective.
Yeah.
Okay.
Yeah, surjection doesn't look for uniqueness. It just says everything in the codomain has to be mapped to.
Okay.
Okay, so in this case, this is one of the extreme examples of something that is surjective. Okay, first of all, is f a function?
Yes.
Is it surjective?
Yes.
Yeah, because the only element in the codomain, which is 1, is mapped to by every element in the domain. In other words, when you count the number of things that is mapped to 1, it is 3. 3 is greater than or equal to 1, we're good.
So it's surjective but not.
Oh, this is surjective and definitely not injective. Okay?
Oh, okay. So that's what.
So with injection, you can say the following. You can say if the cardinality of the domain is greater than the cardinality of the codomain, then f being the function that maps from the domain to the codomain, cannot be injective. But it can be surjective, but it is not guaranteed to be surjective either. Okay? Let me say that one more time. Yep, go ahead.
I was about to say, for it to be an injective, both of the x and y, this codomain and domain have to have the same amount, or can the
In order to be injective, the cardinality of the codomain has to be at least as big as the cardinality of the domain.
Oh, okay. So that means that the codomain could be bigger than the codomain could be bigger than the domain, and it can be an injective, right? Or is it vice versa?
Say that one more time.
Okay. So for it injective, right? For injective, I can have like a medium-sized domain, but if I have a bigger codomain, then it is
It's not guaranteed it's injective.
it is not guaranteed injective, but
It
if I
can
have,
be injective, but it is not guaranteed.
right. But if it's vice versa, let's say I have a bigger domain and oh, never mind, I'm confusing my damn self now. Hold on.
If your domain is bigger than your codomain,
Right.
then it cannot possibly be injective.
Right.
But it can be surjective.
Okay.
But it's not guaranteed to be surjective.
Right. Okay.
Okay, so let's illustrate it. Okay, if the cardinality of the domain is bigger than the cardinality of the codomain, how come we cannot guarantee surjectiveness? Because it seems to make sense, right? Okay, so I'll give you an example. A, B, C, same, and Y is just 1, 2. So in this case, the cardinality of X is greater than the cardinality of Y, right? Oops. There we go. Copy and paste. Now it is not surjective, nor injective. Well, you know it's not injective. That's an easy one because the cardinality of the domain is greater than the cardinality of the codomain. Okay, so we ruled out injection just like that. But we could not have ruled out surjection just based on the cardinality because in this case, it could be surjective if I change the function and have one of the things in the codomain to map to 2. Could have, but I didn't. So that means in this case, it is neither injective nor surjective. It is still a function. Is that okay?
Yeah. So this is surjective. This at the bottom, right?
It is neither.
It's neither.
It
Okay.
is not injective. It is not surjective. It is a function, but it's not injective nor surjective. So any questions up to this point? Be confused sufficiently?
I do, but I don't want to hold up the class time.
It's basically saying that not all the elements in this will ever map out to the elements in Y. For the elements in X, the domain cannot map the entire codomain.
It doesn't have to. Not everything in the codomain has to be used in order for something to be a function.
Oh, for a function, but to be injective.
To be injective, then two different things from the domain have to map to two different things in the codomain. All right. Are we ready to move on, or do we still have any questions? Yep, go ahead.
On the module sheet on the bottom where that's greater than 1, should that be greater than or equal to 1?
You mean here?
Down, right on the bottom. Okay.
Here?
Oh, okay, never mind.
Okay.
Yeah. I only said greater than for some reason.
No, it's cool. Yep.
I was gonna say, just one more time over surjective versus injection, just to make sure that it's all coming together. So if my domain, right, is smaller than my codomain, that makes it surjective, right? Or no?
It cannot possibly be surjective in that case,
Cannot be. Oh yeah.
but it may be injective.
But it might be okay. So if the domain is greater than if the domain is less than the codomain, then it's injection, right?
It is. It's possible it is injective, but not guaranteed,
Not
it is
guaranteed, okay.
injective.
And then all right, and then for surjective, okay, then I got it now.
Okay.
Yeah.
All right. Yep.
So if the cardinality of X is greater than cardinality of Y,
Uh-huh.
as long as the cardinality of Y is bigger than 1, it means that it doesn't guarantee that function to be surjective.
That is correct. Yep. Well, it depends kind of on, yeah. So you're correct. So if the cardinality of X is greater than the cardinality of Y, and the cardinality of Y is greater than 1, then the function is not guaranteed to be surjective. It can be, but it's not guaranteed. But we know for sure in that case it is not injective. Yep.
So basically, what you're saying is that when we compare the cardinalities, we can show what it's not, but we can't show what it is.
Yes.
Okay.
Yep, exactly. So the cardinality of the domain versus the cardinality of the codomain
Yeah.
can only suggest what it cannot be,
No, what
but it
can't
cannot
be.
confirm what it can be.
Okay.
Yep. That is absolutely right. So are we good so far?
Yeah, now we
Okay. All right. So we'll move on to bijection. What do you think bijection means? Both. Exactly. So bijection means it is both an injection and a surjection at the same time. Okay. So once again, there are several ways to look at it. Okay. One way to look at it is to say this. Now you might say, but we have seen something like that already when we first talk about functions. Well, sort of. When we looked at something like this, when we talked about functions, it was not for all q in y. It was for all p in x. Okay, so there's that slight difference. So in this case, we are basically saying everything in the codomain is mapped to from one and only one element in the domain.
It's a one-to-one function.
It's 1-to-1, exactly. So bijection is actually what we want in many cases. In many cases, we don't really have any use of functions being just injection or just being surjection. But when it's a bijection, suddenly we have a lot of interest. And one example of a bijective function, or a function that should be bijective, is when we describe the outcome of a sorting algorithm. That function that maps the index of the array after sorting to the constants defined before the array is sorted, that function has to be bijective in order for us to qualify the algorithm to be a sorting algorithm. Yes?
I'm just curious about the sort some information into an array that's bigger than the actual information. And obviously that was what I'm messing with.
But that's not sorting anymore, right? If the array that you end up with is larger than the array that you start off with, that's not sorting anymore. Sorting has to be the same size. The resulting array and the given array, they really need to be exactly of the same size. There has to be a one-to-one mapping from the values after you sort to the values that you begin with. To count as sorting.
Okay, because if I'm or not clear with the new, it doesn't have any sorted. Or if I was just sorting by
Okay, if your
one,
resulting
six.
array is greater than the original
Not the
array,
amount of information, Joe, just the size, the species.
it still doesn't make sense because then some of the elements will be undefined.
Exactly. So I'm just wondering what
That would not be counted as a correct sorting algorithm. It's an invitation for an exploit attack. Okay, so now that we have understood what is injection, what is surjection, and what is bijection, let's look at some of the cool things we can do with bijection. A bijection is reversible, which is really, really cool in many ways. Okay. Okay, so right here we basically we're just looking at the notation here. So given a bijection f that maps from x to y, there has to exist another bijection which we'll call f inverse. So f to the power of -1 is also known as f inverse, which goes from y to x. So the inverse is going to flip the domain and the codomain. If the original function f maps from the domain x to the codomain y, then the inverse of the same function will have y as the domain and x as the codomain. And then the mapping goes opposite way. Okay? So the inverse has this property. For every element in the original domain, okay, I shouldn't even use domain X anymore and just call it X. Okay. So for every element E in X, if you apply F inverse to F of E, you should get E back. And that property should hold true for every E in X. Is that okay? And this is actually probably not needed. For every element in Y, okay, same thing happens. If you apply F to the F inverse of E, you should get E back. So the order of applying F versus the inverse of F really should not matter. It should still be the identity function itself. Combine those two. Is that okay? So I'm going to ask you a few questions. Is sine a bijective function? Sine as in sine, cosine, as we know. Sine is not a bijective function. Is it a function?
Yes.
But it is not bijective. Why is it not a bijective function?
Because it's not a
It is not surjective, right? It's you're right. It is not injective. Why is it not injective?
because
Yep, you guys got it. So depending on what unit you're talking about, if you use radians, then you pick any x as a real number, x plus n, which is an integer, times pi, times 2 pi, is going to be the same thing. Okay. In that case, actually, it is the same for both sine and cosine. If you're multiplying an integer to a 2 pi, because that's 360 degrees. Okay. Very good. All right.
So those are great terms, like bijective function would be y equal to x.
Say that one more time.
And algebraic terms, y equal to x would be a bijective function.
Yes, because x divided by 2 would then become the inverse function. Yep.
So an inverse can only have a function that is bijective.
Yes. It only makes sense, okay, to have an inverse function when the function itself is bijective. Because otherwise, so the whole point of an inverse is if you give me quote unquote the result of applying f, I can tell you which value in the domain will give you that result. That's the whole idea. It's basically undo, right? It's the same thing as Control Z undo. This is the current document, but how did we get here? Somebody inserted a paragraph here. So Control Z will undo it. Okay. So everything that you do in Google Documents is undoable. So that makes every action you can perform in Google Documents a bijective function, so to speak. And then if you start with a blank document, your final document is a chain of application of functions, and each one is reversible until you get to the paper that you turn in to English Writing 300. Yep.
Wait, so you said if it's not bijective, it's not reversible?
If it is not bijective, then you have one of two problems. Okay, because if it's not injective, then I think about it. If it's not bijective, then it's either not injective, not surjective, or even, right? Okay, so we'll deal with the problem of not being injective. Okay, so if a function is not injective, that means multiple things from the domain can map to the same thing in the codomain, right? So if I say, okay, here's the result of applying the function, what was the starting point? It is possible that you can point to like, oh, that element in the domain can all lead to this one thing in the codomain. That doesn't help, right? Okay. Likewise, if the function is not surjective, then you can pick a value and say, okay, here's the value. Okay, who is mapped to here? Nobody. Okay, so it cannot go backwards either.
I only ask like sine inverse is a thing. But I guess like if you do sine inverse of something, it's like plus the k.
Sine can only illustrate one problem because sine is not injective, so it only has the problem of this is the value of a sine function. What is the angle that leads to this?
Okay.
But sine is also not surjective, right? So that means okay, here's 2. Which angles sine is 2? No.
there's no angle that will give you a sine value of 2. So it actually has both problems because sine is neither injective nor surjective.
I only ask like we do use like inverse sine, inverse cosine.
Yeah, but only within a certain
Like
range.
certain-
Yeah.
okay.
So if you redefine your domain and your codomain,
You define it to be.
yeah, you can
Okay.
make it bijective.
So we have to like make it before. Okay.
Yeah, so you have to make it clear what is your domain and what is your codomain before you can state anything about injectiveness versus surjective. So in the case of sine versus sine inverse, if you say okay, the range or the domain is negative pi to pi, and the codomain is 1 to negative 1, then it is bijective.
Then it is bijective. Then
Yep.
Okay. Okay.
On the other hand, if you say my domain is the real number
Yeah. Then it
and
will-
my codomain is also the real number, then it's neither. It is not injective and it is not surjective.
Okay.
Yep. Back there?
You're you.
Oh, okay. Cool. Go ahead.
So let's say the function f of x equals x squared.
Uh-huh.
That would be surjective, right? Because
F of x is x squared is it cannot be surjective because all the negative values cannot be mapped to, but it depends on what you define as your codomain. If you define your codomain as all the non-negative numbers and your domain to be real numbers, then it is surjective, but it is not injective because if you plug in 1 versus negative 1, they map to the same value. Yep. All right. So any questions at this point about bijection? No questions about bijection? We got about 10 minutes, which is really good because I think there's enough time to illustrate the use of bijection in automated program verification. Yep.
I just wanted to confirm. So, like, if the function is inversible, that means it's bijective.
A function has a inverse if and only if it is bijective.
Okay.
But then it's only within the range and the domain and the codomain that you choose. Because you can tweak the domain and the codomain in some cases to make a function bijective. But if you extend
Like this.
one or the other, then then it's not bijective anymore. Okay. So let's look at an example here. Okay, so let's say this is line 15 in a program of some sort. Okay, doesn't matter what program it is. You have a variable x, and we'll just say that you apply f of x to you apply f to x, and then the resulting value is put back into x. Okay, and in line 16, your program just get a segmentation fault here. Okay, your program crashed. Okay, so when the program crashes, a lot of times you can actually capture the memory of the program in the process, so that you can do the analysis of how this program crashed. So you capture all of the information, everything on the stack, everything, all the variables and whatnot, and but your program crashed, and this is the last moment of your program. So how are you gonna figure out what happened to this program? You know the program crashed on line 16. Line 15 was did execute correctly. So how do I execute the program backwards so that I can go back until I say, oh, it's not supposed to be here. It made the wrong branch to here. It really should have taken that branch over there. So how do I execute a program backwards? Okay. So then the question is, so we know the post condition of line 15. Okay, so let's say the post condition of line 15 is x. X is a particular value. We'll just call it k. Okay, for some constant. You know this because when the program crashes, the segmentation fault is capturing the value of all the variables at a time. Okay. Can I say anything about the precondition of line 15? What would that look like? So,
So now you have to ask a question first, okay? What is X? Is X bijective? Yep, go ahead.
I don't know, I was gonna say if X exists. That's
Yep.
the condition.
So if X is bijective, then you are in luck, okay? So I'm gonna say if if F is bijective, then we can make the conclusion of the precondition of line 15 is that X is not F of K, but F inverse of K. Is that making any sense? Because you're undoing what F did to the original value of X. So now you can execute the program backwards. Okay? And you go like, yeah, but nobody writes program like this, right? I mean, you have all kinds of updates of variables, but very few of those will look like this. Yeah, but it all depends on how we define F. Okay? Most likely, a lot of times, F of X is something that is so simple, like incrementing. Right? How many of you have written programs that increment a particular integer in the program? Okay. So F of X is really just a representation of some kind of function that we apply to X so that the result of that is used again to update X. Okay? So X is changed based on its own original value. Okay, and in programming we do this a lot. Okay? A lot of variables are updated based on its own value prior to the update. But using this technique, we can now execute programs quote unquote backwards. And by doing that, it makes it possible for you to analyze a program and figure out, okay, how did I get here? I'm not supposed to be here, but why am I here? So you can undo the operations to various variables until you get to the point where there's a branch. You go like, oh, I made this branch, that's why I ended up there in a place that you're not supposed to be. Maybe I made the wrong decision. Okay? So that's the way you can, this is a technique that you can use when you're debugging a program. Is to reason your way backwards. Yep.
So if the function is not bijective, then we're pretty much screwed, right?
If the function is not bijective, then you cannot figure out what the value of X was prior to that. Okay? So a function that is not bijective can be just a constant like that. So if you initialize X to 0, then you have no idea what X was prior to the segmentation fault, because at the segmentation fault point, X is 0 because we updated X to F of X. But prior to that, you have no idea what X is. But remember, this is just a snapshot. This discussion is revolving around just one single variable of your entire program. So even if F is not reversible, there are many other variables involved by the time you crash, right? So all of those variables, the last update of every single one of them can help you execute the program backwards and know more about what happened. Is that okay? All right. So that makes it, so we are pretty much done with injection as well at this point. So I just want to make sure that we don't have any lingering questions about injection, surjection, and bijection. Are there any questions about those three? Because we are pretty much done with this, and I can open up this activity on Monday, okay? Which means you got 5 days to kind of study this material before I give you the homework assignment on functions. So if you have any questions, when you're studying this, you're reading the material or watching the video or whatever, and you go like, okay, I'm not really clear about this concept, don't ask me right away. Try to think about it, okay? Try to absorb the material on your own, come up with examples, and then you just basically come up with examples, and then you ask yourself, first of all, is this a function? Okay, this is the domain, this is the codomain, this is F as a set of two tuples. First of all, is this a function? If it is it injective? Is it surjective? Because bijection is easy. It is just both. It is both injection and bijection. Okay. You can also reverse. Okay. Find a buddy in the class. Okay, or find someone who has taken this class before, and then you go, okay,
I'm making an injective but not surjective function. Here it is. And I have the other person to say, okay, is it really the case? So you're coming up with examples, and then you evaluate the example and say, okay, is it injective? Is it surjective? But you can only ask those questions after you confirm that it is a function to begin with. Is that okay? For those of you who are super ambitious, you can write a program to automatically randomly generate mappings or subsets of two tuples, and then you just look at each one that it generates, and then you answer the question. Is it a function? Is it injective? Is it surjective? And therefore, is it bijective? Okay? Do you guys know how to do that?
Not really. I don't know how to get that shit.
Okay, so I'm gonna leave it up to you guys to do it. I can probably do it with a spreadsheet. Okay, just randomly generate something and then you qualify whether it is a function. If so, is it injective? Is it surjective? And if it is both, then it's automatically bijective. All right. So read up the next module if you have time. So if you're okay with all the functions concepts, go ahead and read about relations, okay? Because that's also a kind of important concept in programming. I'll see you guys on Monday. Have a nice weekend. Unless I see you tomorrow because you're also in my 310 class.